Wow, so we've studied a lot of functions already, but in this unit we're going to get two more functions. It turns out they do really go hand in hand, so it won't be too overwhelming. But those two functions are going to be exponential functions and logarithmic functions. So in this video, we'll stay focused on exponential functions. We'll start with those. So it helps to get just a general form down for an exponential function. So let's write our general form as y equals, or f of x equals, and I'm going to write it as a b to the power of x. And just right there, let's pause for a moment and take in the immediate difference between this general form and everything we've seen so far. So if we think back on our polynomial experience, on our rational experience, we have not yet encountered the independent variable being the exponent, right? So this is automatically kind of the different feel of this function. So everything we've studied in the past with polynomials and rationals, we've had the variable being raised to powers, right? Or even, you could have multiple variables raised to different powers, but it's always been that the powers have been numbers and the variable has been the base. So that just flip-flopped here as we start working on exponential functions. So I just wanted to point that out. The other thing, this is kind of just a technicality, but I should say it, is this form is true for any non-zero number a. So a, that little coefficient up front, is a non-zero number. And then b is any positive real number, such that it's not equal to 1. So b is any positive real number such that b does not equal to 1. So those are just the conditions to keep this model exponential, right? If some of those conditions are not met, we just end up reverting back to, a function type that we've already studied. So those conditions will keep it exponential. And let's just dissect this value of b a little bit more. So b is the base for the exponential. And it turns out that if b is greater than 1, if the value of b is greater than 1, we will be looking at an exponential growth model. So if we're talking about, population or investing money, we would likely see a growth model. I guess with population, you could see decay if it was like an animal that was being hunted or something like that. So if b is greater than 1, we look at exponential growth. Now, if b is between 0 and 1, right, we already said that b needs to be a positive real number. So if b is between 0 and 1, not including either, then we'll be looking at an exponential decay model. And I think this is a fun time to bring up nuclear medicine, just because I know several of you will go into that field, right? You guys will be focused more on the decay side of the house than the growth. If you put an amount of a nuclear substance into somebody, you don't want that amount increasing, right? It's going to decay over time. So that's just kind of cool. A couple more characteristics in terms of looking towards graphing. We'll spend another video focused strictly on graphing, but let's just talk about the domain and range of the base graph. So it turns out for exponentials, the domain will be all real numbers. And the reason being is when we look at this model of y equals ab to the x, right, you can stick any input you want in. You can take anything, you can take a base and raise it to any power. So the domain is all reals. Now the range is not all reals, and we can talk through why that is, but the range could be expressed as 0 to infinity if the a value is greater than 0. So if we talk about this value of a up front, this goes back to our understanding of transformation. So basically we're saying it's not reflected. And then if a is less than 0, the range flip-flops to negative infinity to 0. This is again assuming no other, vertical transformations have occurred. So that will be the range. And we'll look at the graphing as I mentioned in another video, but it's easy to state those conditions right out the gates here. The y-intercept is another super clear point that we'll use frequently, and that is because we understand from the past to find a y-intercept, we're plugging in 0 for x. So if we think about plugging in 0 into this model, 0 becomes the exponent, and anything to the power of 0 is just 1. So that means we get a times b to the 0, which is just 1. So the y-intercept is easy to find. It's just at a. So the y-intercept is 0, comma, and then whatever that a value is. So I'm speaking in a very general form here. We will get more specific soon. Last unit we talked about asymptote. So let's just mention horizontal asymptote is a characteristic of this graph. And again, for the base graph, I'm talking just about the base graph, the asymptote would be at y equals 0. So that just starts getting us a little bit more comfortable with what these graphs are. I'm going to snag one in Desmos real quick just to start building that connection between what we just mentioned here and the graph. And then we'll do a little bit with writing exponential functions. All right, I got a little excited about the graph, so I'm going to actually share 4 graphs with you. But when people say, draw me an exponential graph, probably the knee-jerk reaction is going to be something like what I'm showing here in blue. So the equation of this blue line is y equals 2 to the x. So the reason I say that is the value of the base is greater than 1, so it's demonstrating an exponential growth. And then it's not reflected at all about the x-axis. So that's probably what most people visualize, right? If you were investing money, you would want it to grow most like that blue graph than the orange, purple, or green. But in immediate contrast to the blue graph, I went ahead and graphed in orange y equals 1/2 to the power of x. So the only change I did there, as you can see, is I changed the base from 2 to 1/2. 1/2 is less than 1, so that's why that graph is showing decay, right? We can tell that that graph is falling from left to right. So that would be a decay rather than a growth. And then, as you might expect, the 2 graphs on the bottom in green and purple, those are just me taking the blue and the orange and reflecting them. So the green graph would be the reflection of the blue graph because the equation of the green graph is y equals -1 times 2 to the x. So I made the a value negative, so it sent it below the x-axis. And then the purple graph is basically the orange graph reflected. So it has the equation y equals -1 times 1/2 to the power of x. So just to start getting familiar with the way exponential curves look, right? So using different bases and then using different a values, we can get them to kind of move all around the coordinate plane. But when you close your eyes and picture an exponential, probably, as I mentioned, this blue graph is a good base graph. So you can see that horizontal asymptote in here at 0. You can see the domain of all real numbers. You can see the range for the blue graph being 0 to infinity. So I hope that just gives you a little bit of an introduction to exponentials. Go ahead and watch the next video to see how we can write exponential functions when given a little bit of data.